You- You're asking something? Yes, tell me. So today basically we will just recap whatever we have learned so far. Okay, so from the very beginning, so few topics we will discuss from the from the very first class to week 12. Okay, so it will be a kind of revision. Okay. Okay, so first we'll discuss about the stability conditions that we have learned in our initial classes. Okay, so what is the unstable condition was if suppose there is a pack of air and that is so pack of air having temperature of 15 degrees centigrade, and if the surrounding temperature is below that, suppose if it is 10 degrees centigrade, so the warmer as this air packet is warmer, so it will keep on rising. Okay, so until its temperature is equal to the temperature of the surroundings, so it will keep on rising, so that's unstable condition. Okay, so this is in this figure you can see uh, this, and for stable condition, if the temperature of this air packet is lower than the surrounding temperature, it will not like, so it will be denser compared to the surroundings. So that's why it will sink. Okay, so as it is denser than the surroundings, it will sink, so it will not rise, so it will try to settle, so it's a stable condition. And neutral condition is when the temperature of the air parcel is similar to the surroundings, so it will not like, it will stay in its own position, so it will not rise or sink, so and this condition is neutral condition. Okay, so then we learned about the different stability conditions. So so the stability is dependent upon the environmental lapse rate and dry adiabatic lapse rate, saturated adiabatic lapse rate that we have learned. So so whatever the environmental lapse rate, we just compare it to the dry adiabatic lapse rate or saturated adiabatic lapse rate to find out whether the condition is stable or not. Okay. So basically in troposphere, the temperature of the ambient air that decreases with an increase in altitude. In this figure, you see the temperature is in y-axis, it is height, and x-axis it is temperature. So the temperature is will keep on decreasing with increase in height. Okay, so and we consider the pollutions and all, we generally consider in the troposphere region as we are living in it. So the rate of change of temperature is called lapse rate. Okay, so if T2 minus is if T2 minus T1 by Z2 minus Z1, so basically delta T by delta Z that we calculate to find out what is the lapse rate. Okay, and this environmental lapse rate, it is observed by using radio sound. Okay, it's basically a battery powered instrument that is carried to the into the atmosphere by weather balloon that measures various atmospheric parameters. Okay, so in this figure you see this is a balloon, and this radio sound, it is carried by this balloon. Okay, so adiabatic lapse rate, so it is the rate at which the temperature of an air parcel changes adiabatically in response to the compression or expansion associated with elevated range. Okay, so suppose this is the air parcel with increase in height. What is the change in temperature? So adiabatic, as it is an adiabatic process, so no heat exchange occurs. It is assumed that no heat exchange is occurred between the given air parcel and its surroundings. Okay, and there are basically two types of adiabatic lapse rates. It's dry adiabatic lapse rate and wet adiabatic lapse rate. Okay, and the dry atmosphere is like when the relative humidity is less than 100%. Okay, so in that condition, that is the air parcel is unsaturated. Okay, so that is dry adiabatic condition, and in this condition the lapse rate is 9.8, or sometimes it is mentioned as 10 degrees centigrade per 1000 meter. Okay, so here see in this case, so it is considered as 10, so in 1000 meters, so this 30 degrees centigrade has decreased to 20 degrees centigrade, then 10 degree into 1000 meter height. So the dry adiabatic lapse rate is 9.8, and it is mentioned as DALR, and wet or saturated adiabatic lapse rate when the it is when the relative humidity of the air parcel is 100%. Okay, so and that is the saturated condition, so or moist condition, and in this case the adiabatic lapse rate, the saturated adiabatic lapse rate, it is 6 degrees centigrade per kilometer. These values you have to remember. Okay, so if any questions are asked, you can answer. So atmospheric, so the role of ELR, that is environmental lapse rate, and adiabatic lapse rate, so depending upon these relations, so different stability, like different conditions are there, like super adiabatic lapse rate, sub adiabatic lapse rate, neutral, negative or inverse state. So super adiabatic lapse rate is nothing but when the environmental lapse rate that exceeds the dry adiabatic lapse rate. Okay, so that is 9.8. Okay, dry value is 9.8 or 10. So in this figure you can see, so this is the slope. This slope is, this is ELR. Here the here we have to calculate what is the slope of this straight line. So if you calculate this, the slope is greater compared to this one, DALR. So that's why, so we can say that here in this figure, the environmental lapse rate, that is ELR, that exceeds the dry adiabatic lapse rate. Okay, so so whenever you see such diagrams, you have to find out what is the think. You have to think what is the slope. What will be the slope? Which slope will be greater? So then you can you will be able to easily understand this. Okay. So this is super adiabatic condition. Here the environmental lapse rate exceeds the dry adiabatic lapse rate. Okay, and sub-adiabatic condition is the opposite one, when environmental lapse rate is less compared to dry adiabatic lapse rate. Okay, so this is sub-adiabatic lapse rate. In this figure you can see, and neutral condition is when these two lapse rate are almost equal. And inverse condition is like when environmental lapse, so in troposphere with increase in height the temperature is decreasing. So inverse condition is when with increasing height the temperature is increasing. So when such conditions occur, that is called inverse condition. Okay, so when the air temperature increases with altitude, then the lapse rate becomes inverted or negative. So sometimes it is also called negative lapse rate. Okay, so these are different lapse rates, and depending upon these conditions, Different plume behavior you will see. So you can expect questions from the plume behavior because it is an important thing. So these are the different plumes. Okay. So first one is the looping plume. So in this case, you see the ELR, it is environmental lapse rate, that is greater. So the slope of the straight line is greater compared to this straight line. Okay. So ELR is greater than ALR, that is adiabatic lapse rate. So generally you consider the dry adiabatic lapse rate. Okay. So when ELR is greater than ALR, that is when super adiabatic lapse, super adiabatic condition. Okay. So this condition. So when this condition occurs, then the plume behavior will be looping. So it will like uh, come near to the ground. So it will like disperse like this. Okay, and fanning plume is when the inversion condition occurs. Okay, so then the plume behavior will be like this, very less dispersion, and coning plume is when so nearly when the stability condition is nearly neutral. Okay, so like environmental lapse rate is very close to the adiabatic lapse rate. So in that case, coning plume will occur. Okay, and lofting plume, here it is when the inversion is below the stack height, inversion occurs, inversion condition. So in that case, so this plume will go like so it will not come at the ground level. So because in inversion condition very less dispersion occurs, so uh, it will go above this stack height and it will not come to the ground level. And lofting plume is inversion and then like any other condition, either it is super adiabatic or subadiabatic. So in that case, and this is the ideal condition. So in this case, no ground level concentration will be observed. Okay, and next is fumigating plumes. So in this case, it is the opposite of this lofting one. So in this case, the inversion layer is above the stack height. So it will not, so the plume will not go above this stack height. So it will just come like below this, like it will disperse below the stack height. And it is the worst scenario. So you will observe like maximum ground level concentration of the pollutant you can observe. Okay, and next is the trapping plume. So in trapping plume, like inversion layer, so when inversion layer before and above the stack height. Okay, so here below this line, inversion layer is there, and above this line, inversion line is there. So no dispersion will occur in these two region, and the plume will be trapped in between this. So this is trapping plume. Next is neutral plume. Neutral plume is when like both the lapse rates are equal. Okay, then the plume will like look like this. So it will go straight up. So and this is a Pascal Gifford stability classifications. So depending upon what is the surface wind speed, that is like up to 10 meter, what will be the wind speed, based upon that, and the timing, daytime, nighttime. So based upon the timing, these are the different stability conditions mentioned. Okay, so it is basically with like related to whatever the wind speed, depending on the wind speed and the daytime or nighttime, what will be the stability condition. And these stability classes are there. So different stability classes from A to G, and what are the nature. So if the stability class is A, so it is considered as very unstable. If B, then moderately unstable. If C, then slightly unstable. So like this. So different stability classes are there. So while solving different like numericals, you may like you need to know what is the stability condition. Okay, so to find out what will be the like different coefficients values from the chart. So basically you will get those values in the exams, but still to understand this, what will be, these are the stability classes, and depending upon the wind speed, what will be the stability classes are mentioned in this table. Okay, so next is design of stack height. Okay, so for particulate matter, this was the equation. So and remember one thing, this QP, this is in tons per hour. Okay, so you have to express this value. If it is given in any other unit, you have to convert it into tons per hour. And for sulfur dioxide, this is the equation, and in this case, it is not tons per hour; it is in kg per hour. Okay, so depending upon the equations, you have to change the parameters. Okay, like parameter units. So basically the minimum values for chimney for industrial in general, so except for thermal power plants, it's generally 30 meter, and for power plants above 200 megawatt and below 50 megawatt power capacity, then it will be 220, and more than 500 megawatt capacity it is 275. Okay, so these are the minimum values of stack height. And when like plume is like so when plume is getting released from the stack, so it will like go up to a certain height, then it will start dispersing. So then plume behavior you will see. So first it will go up to some height, then the dispersion starts. Okay, so and that height is called plume rise. Okay, so mostly to calculate this plume rise, so this Holland's formula is used. Okay, so this is the Holland's formula. So we also solved some numericals in previous interactive sessions using this equation. Okay, so you can see those numericals. So basically delta H is the plume rise you have to calculate, and Vs, it is the stack gas exit velocity, like with which velocity the stack gas is getting released from the this stack, and D is the inner diameter of the stack. Okay, and U is the wind speed at that height. Suppose if the wind speed is given at 10 meter height, so you have to change whatever the wind speed at that height. Okay, so suppose stack height is 200, so then and the value of the wind is given up to 10 meter height. So you have to calculate what will be the wind speed at that height, that 200-meter height. So that you have to calculate, and these are the values are these are, and this P is atmospheric pressure and it is in millibar. Okay, and Ts is stack gas temperature, and A is atmospheric or ambient temperature at stack height. Okay, so this is the equation to calculate what will be the plume rise. So the effective stack height will be nothing but this H value, the stack height plus delta H. Okay, so this is one numerical discussed in the class. Okay, so an industry that utilizes zero point 0.3 million liters of oil fuel per month. Okay, so it has also been estimated that for every 1 million liter of fuel oil burnt in the factory per year, the quantities of various pollutant emitted are given as follows. Okay, so these are the pollutant concentration given. Uh, so you have to calculate the height of the chimney required to be provided for safe dispersion of the pollutant. Okay, so this equation was given previously. So this is basically the equation, and QP is in tons per hour. So it is given that the for 1 million liter, so these values are given. So for zero point 0.3 million liter per month, so for 12 months it will be 12 into zero point 0.3. So it is just like calculated. So what will be the emission per year? Okay, sorry. Yes, what will be the or for 1 million liter this much emissions are observed. So for 12 into 0.3, that is 3.6 million liter, what will be the concentration? This is calculated, nothing. So and also assuming 300 working days in a year and 24-hour working. So this is so this QP value, it is, sorry, it is this sum. Yes. So this is the total requirement, and for ton per hour. So in this equation, right, so you have to like convert it into ton per hour. Okay, and you got the value in ton per year. Okay, so here there is a typing mistake, so this will be ton per, not year, it will be ton per hour. Okay, so it is considered as 300 working days and 24-hour working period. So QP value is, so in a year, so how much hour in a year, it is just calculated here. So total value, total tons of emission per total hours, it is just divided here, and this is the QP value in tons per hour. And this value is, if you put this value, you will get this is the, and for SO2 emission, this was the like this was the equation. So similarly, it is mentioned in tons per hour, so you have to convert it into kg per hour. Tons per hour value you got, so sulfur dioxide is there 60 ton per year. So similarly, like this, you have to calculate what will be uh, the concentration in uh, kg per hour, and if you put this value, and you have to compare which one is the greater one. Okay, so here you got 12.67, whatever you got in the, by this equation. So compare these two, and whatever if this is the greater one, so what the greater value will be the answer. Okay, so between these two, whatever the greater value, that will be the answer. Okay, so by this way you can calculate the stack height. The next is air quality index. We also learned, this is also an important topic, so you can expect questions from here. So air quality index, it is defined as an overall scheme that transforms the weighted values of individual air pollution related parameters. So for example, so different concentrations are there. So the weighted values of individual like concentration, so air pollutant or pollution concentration, so that is converted into a single number or set of number. Okay, so basically the concentration, for concentration you are getting a, for a certain concentration you are getting a certain number. Okay, so that is air quality index. So basically we follow this in India, we follow the CPCP method, and in this case the air quality index ranges from 0 to 500. Okay, so this is commonly, this is just to find out the level of severity of the air pollutant in public, and higher the number, the greater is the health risk. Okay, so this is the equation by which you can calculate what is the air quality index. Okay, so yes. So no, you can't say fully objective because MCQ type questions will be there, but like in assignments you solve some numericals also. Okay, so like those questions you can also expect some numericals, some multiple choice questions like that. Okay, so yeah, yes, yes. that may come, not directly you can get, like similar questions you can get. So if you like go through once those PPTs, so some sort type questions you can expect. Okay, so direct those questions may not come, but sometimes it comes. Okay, like, but not every question will be direct questions. Okay, so you have to like go through the lectures, uh, PPTs properly. Solve some numericals. Numericals you can expect. So whatever is discussed in the class and whatever like in interactive sessions, whatever the numericals were discussed. So it will be not accept those. But this short type MCQ questions. So that may not come like from directly from the assignments. Some different questions may come. Okay. Objective question. Objective question. So in like previous interactive sessions, I have like shared those PPTs, objective questions, and other TAs they are also like you can get objective questions from their PPTs also. So go through those things and the text whatever like whatever discussed in PPTs. Okay. Sir, whatever sir discussed, so just go through this. So those questions are generally directly like if you see those MCQ questions, if you're from old course or like whatever the TAs they discussed. So these are directly taken from the text. Okay, so it's nothing like text in. So what I'm not getting. So you want the PPTs? For study, see, I don't have I haven't prepared any other questions from like any other MCQs. So it is whatever we are having right now is whatever I have discussed, that is with me. So except that it is I personally don't have. So then I have to like separately I have to prepare. Okay, so that will take time. But you just see the pattern of the question is nothing but whatever is there in the text. Okay, so you can sometimes you can see the highlighted portions. So those are important things. Okay, so important portions are highlighted in the PPT itself. So if you see, you can get. Okay, so air quality index. So if you want to calculate, so this is the equation. Okay, so where IHI and ILO, these are the air quality values corresponding to this breakpoint concentration. So BHI and BLO is breakpoint concentration at higher or equal to the given concentration or lower or equal to the given concentration. Okay, and in respect to this, whatever the air quality index values, so these are IH1 and ILO, and CP is the pollutant concentration that is given in the question. Okay. So using this, you can calculate what is the air quality index. So, so this was one problem that was discussed. Like, see, these are the like different breakpoint concentration and what in which category they are uh, from which category this from so which air quality index category they are falling. So that is mentioned in this table, and we in India generally this follow this table. Okay, so this is CPCB standard, and for there are different categories like good, satisfactory, moderate, poor, very poor, severe. Okay, and based upon that and the air quality index range is also given here. So 0 to 50, 51 to 100. So this is the air quality. So suppose any concentration is falling in this, falling in this category. So this lower limit and upper limit value, this is 100 is the upper limit and 51 is the lower limit. Okay, so in this equation, so this H1 is suppose satisfactory condition, then H1 will be like 151 like this. So you will get to know in this numericals. Okay, so air quality index. So I have to calculate the air quality index for this pollutants. Okay, so this is the equation and concentrations are given. So for PM 2.5, this concentration is given. So this is the CP value. Okay, so and it is falling. If you see from this chart, this is for PM10. Okay, so if you see this chart, this is for PM 2.5, this condition. So good condition. So it is within 0 to 50. Okay. Sorry, this is PM10. This is PM 2.5. So this is satisfactory condition. So this is the range 51 to 100. So uh, the range you will consider will be satisfactory. So 50 to 100. Okay. And with respect to PM 2.5 concentration, this 30 to 60 microgram per meter cube. So this is there. Okay, so if you see the put the values in this equation, so this is this is the so this is the condition. So that this air quality range is from 51 to 100. So that's why this higher limit is 100, and here it is taken as 50, and here the higher limit is this in this region, this 31 to 60. This is the concentration, breakpoint concentration. Okay, so this limits, this higher limit and lower limit is taken, and CP minus BLO. So CP is given as 33 and BLO is the lower level concentration, breakpoint concentration. So minimum breakpoint concentration, so it is 30. Okay, so if you calculate this, and ILO is again it is 50 they are taking. So if you calculate this, you will get 55. Okay. So similarly, for other as for other pollutants, for suppose for PM10, the concentration is given as 63. So it is also falling in this satisfactory this range. Okay. So here also this IH1 and ILO, this will be 150, and see the breakpoint concentration is also this 51 to 100, this range. So here also 100 to 50 they have taken 150. So if you calculate this, you will get what will be the air quality index. Similarly, if you solve for others, for SO2 and for carbon monoxide, you will get different air quality index values. So at the end, so the overall will be the maximum of whatever you got. Okay, so maximum you got is for this 63 value. 63 was, this is for PM10, I think. Yes. So PM10 you got. So this is the so whatever the so the greatest value you have to take. So that will be the air quality index for this, for a air parcel that contains these different pollutants. Okay. So next we learned about the different this Gaussian dispersion model and all. So Gaussian dispersion model is the important one. So you have to like remember the equations. Okay, so this equation you have to remember. I don't know they will provide the equation or not. I don't think they will provide these equations, so you have to memorize this. So so generally ground level concentration we like to calculate from the plume behaviors. So at ground level, so this is z equal to, so in xy z is the vertical, like, so x is the horizontal, y is the x in xyz plane. So z is the vertical portion, and we are, as we are considering at ground level, so z is 0. So this is the equation. Okay, so sigma y sigma z are Pascal before stability like coefficients. Okay, so this is for like ground level concentration, and for center line this y will be 0. Okay, if you want to calculate the concentration at the ground level and at the center line of the plume, then y will be, so y is the like if it is not in center line, so okay, so let me show you the well, so so in this case, if you see this, these are the different directions. So x is this direction. So basically if you want to consider what is the concentration at the center line, so in this case, so this is y direction. So if you want to calculate at center line, then y value will be 0. So at ground level this z value, so at ground level this is the vertical direction z. So if you want to calculate the concentration at ground level, so then z value will be 0. Okay, so these are the different conditions. So if this value is 0, this y value is 0, then this will be the equation. Okay, so this is nothing but here we are putting 0 here, so you will get this equation. And for maximum ground level like concentration at the center line. Okay, so in that case, so it is given this sigma z value. First you have to calculate the sigma z value from this equation. So this is h by root 2. So the h is here, h is the stack height. Okay, so suppose it is asked that the maximum ground level concentration you want to calculate. So for that you have to first you have to find out at which distance this at which distance that is what will be the x value in which distance this condition like maximum ground level concentration you will get. So for that first you are using this like equation, you have to find out the sigma z value. Then from the chart, from this chart, okay, so this is first report, this is the stability chart. So sigma z value for this is from the second chart. Sigma z value can calculate from the this previous equation. Then from this equation h by root 2, then put sigma z value here. So this is the x distance. So with respect to whatever condition, stability condition a b c d e f, so using that curve and this sigma z value you will get what will be the x value. Okay, so using that you have to then after by using these equations you have to calculate. So x value if you get, you will easily get the sigma y value. So x value you get from this chart, then x value same x value put in this chart, and for the same stability condition what will be the sigma y value you will get. So like that, if sigma z sigma y value you know, then using this equation sorry this equation because center line, so this equation you will be able to calculate what is the concentration. Okay, so and one more thing, concentration at the ground level. Okay, if you want to calculate, so when the source is at the ground level, okay, so here is source is the stack. Okay, so elevated source is here, so h value you will get, h is the stack height. So if the source is at the ground level, then this term will also become zero, this h value will be zero, so this term will also become zero. Then equation will look like this. Okay, so this will be the condition when source is at the ground level and you want to calculate the concentration of the pollutant at the ground level and at the center line position. Okay, that is Z0, Y0 and H0. So in that case, this will be your equation. So these equations you have to memorize. Okay, so basically this is the important one. If you understand other situations, so if you remember only this equation, you can like easily convert it to any other equations. Okay, and maximum ground level concentration like this. If you know the maximum ground level concentration, so x value you get from this equation from this sigma z value, and using that x value find out what is the sigma y value and put this in this equation, you will get maximum ground level concentration at the center line. Okay, so yes, this is the like wind speed at different height. Okay, so suppose wind speed, so in previously I was telling you in that Holland's equation, so you have to find out what is the, so in this equation I was telling you if wind speed is given at 10 meter and stack height is 200 meter, so you have to calculate what will be the wind speed at 200-meter height. So using this equation you can find out, sorry, so using this equation you can find out what will be the wind speed at any other height. Okay, so u0 is the wind speed at instrument height, okay, at which height it is measured, and uz is the wind speed at plume height z. So this one you have to calculate. So it is nothing but z by z0. Z is the effective stack height. Effective stack height is that h plus delta h that I mentioned earlier. Okay, so h is the stack height and delta h is the plume rise. So effective stack height is h plus delta h. So this effective stack height is z, and z0 is the instrument height, and p is that factors that depends on the stability condition of the atmosphere. Okay, Suppose this is the table for these are the different stability classes and the p values are mentioned. Okay, so for urban area or rural area, so what will be the p value you can get from this chart, and using these p values you can like get what will be the wind speed at a certain that desirable height at which height you want to measure. Okay, and these are the stability charts. Okay, for horizontal dispersion and vertical dispersion. So this is one simple problem, simple numerical that to understand the Gaussian flow model, Gaussian dispersion model. Okay, so okay, so a stack height in an urban area is emitting 80 gram per second of NO, and it has an effective stack height of 100 meter. The wind speed is 4 meter per second at 10 meter. So at 10 meter the wind speed is given, so you have to change it to what will be the wind speed at what will be the wind speed at this 100-meter stack height. Okay, effective stack height. So and it's mentioned that it's a clear summer day with the sun nearly overhead. So you have to estimate the ground level concentration at 2 kilometer downwind distance on the center line, and if it is and at 0.1 kilometer from the center line. Okay, so first, so the description this for this description, the stability class will be stability class B. Okay, so clear summer day will sun nearly overhead, and this wind speed is in between 3 to 5. That's 4 meter there is given. So in between 3 to 5. Uh, so the stability class is B. Okay, so and you have to determine so what will be the sigma y and sigma z value. Okay, from this chart. So x distance, this is 2 kilometer. So in here, so in 2 kilometer, and using this chart, you can find out what is the sigma stability condition. B. So using this, you can find out what will be the sigma y and sigma z value. Basically, in exam, the sigma y and sigma z values will be given. Okay, so you don't have to calculate from the chart. But for understanding, so just understand how it is. These values are generated. Okay, so wind speed you have to calculate from this height. So suppose for so it is mentioned at 4 meter per second, and at 100-meter height, what will be the speed? It is calculated, and yes, this is the like stability class B is moderately unstable, and for this condition, this p value will be 0.15. Generally, this value will also be given. Okay, so the p values. So for the first case, at the center line position, what will be the concentration at ground level? It is asked. So y is 0, x is 2000 meter. So if you put these values here, so 80 gram per second it was mentioned, and whatever the value is, 80 gram per second. Okay. So if you put these values here, you will get the answer as this much, 64.3 microgram per meter cube. Okay. And for the next condition, it is mentioned that zero point 0.1 kilometer away from the center line. So 0.1 kilometer is 100 meter. So here this term will also come. So y term. Okay, so this is not zero here. So if you calculate this, you will get this is the concentration. So see the at the center line position, you will get the maximum you will get a greater concentration compared to whatever the concentration away from the center line. Okay, this is due to the dispersion. So next, for this was for the earlier it was for the point source, and then for the line source, this is like vehicular emissions generally. So this is considered as line source, and in this equation you have to like remember. Okay, so this is concentration at the concentration for line source in Gaussian dispersion model. So for let's understand this with the help of a numerical. Okay, so you have to estimate the total hydrocarbon concentration at a point 300-meter downwind from an expressway at 5:30 p.m. Okay, so and it's an overcast day. The wind is perpendicular to the highway and has a speed of 4 meters per second. The traffic density along the highway is this 8,000 vehicles per hour. The average vehicle speed is 4 miles per hour. The average vehicle emission rate for hydrocarbon is this much. Okay. So if you see the calculation, so the number of vehicles per unit length you have to calculate. So vehicles per meter, so this was the number of vehicles, and this was the speed. Yes, vehicle speed 40 mile per hour. So if you like vehicles per meter, this is per unit length, what is the number of vehicles you have to like, calculate. So the emission rate is this q is emission rate, so gram per second per meter. So if vehicles per meter is this much, okay, so this is vehicles per meter and this is the emission rate. Okay, so if you multiply this, you will get per meter length what will be the emission. uh, okay, so again the overcast day, the stability class is D. Okay, so and from this figure, so again these values will be given. Okay, so this sigma y sigma z values, I think it will be given still for understanding purpose. So this is for stability class D. See this line, and x is the distance. Okay, so the concentration is about 300 meter. So from this plot, so at 300 meter, what will be the like sigma z value? You can find out from here. So if you put this in this equation, so here the source is at the ground level, so this h term is 0. So this is the term that you have to use. So this, if you put the values here, so you will get this so 42 microgram per meter cube as the answer. Okay, next is the area source. So in this case, virtual point is you have to calculate the virtual point. Okay, so suppose this is an area, so this is the side, so square area is considered generally. So this is the side of one this one side. So basically you have to like calculate what is the virtual. So this area source is converted into a virtual point source. Okay, and then the concentration is calculated at the desirable distance. Okay, and the initial spread it can be given as, so this see here this sigma y0. Okay, so for this portion the sigma y0 is s by 4.2. S is nothing but this the length of this side. Okay, so using this s by 4.2, you will get this sigma y0, this value, and this is the distance x0 from, and this is from the center line of this area. Okay, So next is for a given stability class, x0 can be known for the corresponding sigma 0. So sigma 0 value you calculated, okay, by s by 4.2, and using this sigma 0 value from this chart you can get, and the stability condition, you can get what is the x value. Okay, so x value, and this is nothing, it is not only the x value, this is the x0 value. Okay, so this is nothing but this distance. So the x value you will get, this is the x value, this distance, so this x0 value. And suppose you want to calculate the concentration at this distance r, and that is at distance xr from the center line. Okay, so then the total distance from this virtual point source will be nothing but x0 plus xr, and that is what it is mentioned here. Okay, so first you have to like find out what is the x0 value, and then the total distance will become x0 plus xr. So a new x value you will get, and again using this new x value from this chart, you have to, from this x value, using this x value from the chart, from this two chart, the sigma y and sigma x, sigma y value and sigma z value chart. So using this x, you have to find out the new sigma y and sigma z value. So in this problem you will understand properly. So this is the upwind of Taj Mahal. There is industrial area which has area source towards polluting the national. So the quantity of emission is this much, 100 kg per hour, and mean velocity at height 30 meter is 4 meter per second, and side of the area source is given as 500 meter. Okay, so A's value is 500. Okay, so sigma y value you have to calculate by is by 4.2. So 500 by 4.2 you have to do. You have to calculate the concentration of the pollutant from the industrial area. Take a distance. So at 400-meter distance, you have to calculate. So see this is this xt. So this is 400 meters. So at this point t, you have to calculate what is the concentration. So for that, first you have to create a virtual point source, and what is the this x0 value you have to find out first. Okay. So basically, so similar. So sigma y zero value is 125. So using this value, sigma y value, and the stability condition. So here it is, stability condition is E. It will be mentioned, and these values will be given. And so for 125 meter of sigma y value, what will be the distance x? So that is the x0. The new x value will be 2800 plus 4000. So this is the new x value. Using this x value, you have to find out what is the new sigma y and sigma z value, and this is mentioned. So this is calculated here. So what will be the new sigma y and sigma z value? Then, so at the center line, the concentration you want to calculate. So y value, y term will be 0. So this is your equation. So if you put the values, all the values in this equation, okay, so you will get. So generally it was mentioned, the concentration was mentioned in kg per hour. Okay, so you have to convert into gram per second, and then so you will get, so this much microgram per meter cube. Okay. So any questions till now? Yes. Yes. I'm not getting. Can you please write in the chat box? Okay. Okay, so one was asking about research topic. Is it related to like air pollution and control or any other? Okay. See, you search if for there are like different treatment process. So you can take from solid waste. Okay, so e-waste and all like plastic waste management based upon that. And if for wastewater treatment, there are several researches are going on like contaminant of emerging contaminants. Okay, so that you can also see. So there are different processes like biological process or like any other advanced oxidation process. So these are there are different processes to like mitigate those things. Okay, so see these topics like first you have to like decide like in which area you are comfortable like in bio if especially for wastewater treatment, is it biological method or like or like uh, any other chemical method or any other like advanced oxidation process like that. So first you have to decide based upon that. And for like waste like solid waste management. So you have to fix what is the waste. Okay, so there are different kinds of waste like agricultural waste, e-waste, and different kinds of waste. So first you have to think about that, like in which waste you have to do literature first. Okay, you can if your supervisor is decided so who is your supervisor, is if it is decided right now, so you can talk to your supervisor also, like first you have to do some literature to find out in which area you are comfortable. Okay, so then you have to decide based upon that. Okay, so okay, so my masters was related to like biological treatment of wastewater. Okay, so I worked with dairy wastewater and also it was basically constructed wetland. So it was a different thing, and many people also work in advanced oxidation processes. Okay, so photocatalysis and all. So these are different things. First, you have to do literature and find out what is the where you are like where you feel comfortable. Okay, so then you have to decide. So you can like discuss with your supervisor also, but first go with some basic idea about different fields. Okay, so in fields you want to work, so then you can discuss with your supervisor. Okay. Yes, I worked constructed wetland, so vermifiltration basically. Yeah. So you can it's published already, so you can see if you see my Google Scholar profile, you can see. Okay, so right now I'm working in different field. So it's anti-corrosive coatings, and also I'm working right now. So it's a different thing. So you have to decide first. You have to do some literature and like find out which topics you want to work. Okay, so first, like you have to decide what is like you want to work in wastewater or air pollution or like any other topic like solid waste management and all. So first you have to decide those things. Then you have to go for the topics. Okay. Okay. So next is, so we learned about some indoor air pollution. Uh, so indoor air pollution. So it was like indoor air quality. So you have to understand, like know about the indoor air quality within the buildings and structures. So basically, because it relates to the health and comforts of the people who are living inside the building. Okay, so so there are some common indoor pollution sources are like this tobacco smoke, building materials. Okay, so varnishing fabrics, glues, cleaning products, combustion appliances like cooking and heating, open fires, so living organisms. So this schematic shows the different primary sources. Okay, for uh, bedroom, garage, bathroom, okay, kitchen, living room, basement. So these are the different, like what are the sources and what are the primary sources of the pollutants you can find out. Okay, so this is generally from this household. So what are the different pollutants can have? So indoor air pollution, how indoor air pollution can occur. So outdoor air pollution pollutants can enter in the building, and these chemicals from a modern building and furnishing materials. This also will contribute to indoor air pollution. So combustion gases from fireplaces and wood burning stoves from the kitchen. Okay, or furnace area. So this will also contribute to indoor air pollutions. So carbon monoxide fumes from garage. So carbon monoxide is generally like released due to the incomplete combustion of the fuels. Okay, so that will like So it will be present in the garage and it will contribute to indoor air pollution. Cigarette smoking, okay, so if like radon is present, so radon also can penetrate through the like foundation and enter in the building. Okay, so and chemical fumes from paints and solvents, and this will also contribute to indoor air pollution. Okay, so these are some health effects. So like no, NO2, if it is present, it will cause irritation to skin, eyes, throat, cough, and sulfur dioxide, it will cause a lung disorder and shortness of breath. So carbon monoxide, headache, shortness of breath, and may cause sudden death because like it will like attach with hemoglobin and it will reduce the transfer of oxygen. Okay, so it can cause sudden death. Pesticides can cause skin diseases. Okay, and formaldehyde, so this, irritation to skin. VOC is the liver kidney disorder, irritation to eyes, and also ozone. So it will also like cause respiratory disorder. So it lowers the resistance to cold and pneumonia and all. So this radon and this suspended particulate matter that may cause lung cancer. Okay, so these are some common effects. So you also can like in this lecture it was discussed about different effects, okay, health effects of in like precisely it was discussed. So you go through this because effects related problems questions may come. Okay, so so you can improve the indoor quality by like pollutant source control. You can control at the source. You can increase the ventilation, dehumidification, okay, using different cleaners, dust collectors, and filters, etc. So uh, these are some common pollutant source control measures. Okay, so you can ban smoking or limit smoking in smoking well ventilated areas. Okay, so by improving ventilation, so ventilation can be improved naturally or mechanically. So naturally or mechanically. So these are mechanical ventilation. So this involves the use of fans, air conditioning systems, etc. Okay. So indoor air quality model. So box model I discussed. Okay. So this is a basic mass balance approach to derive the concentration of the pollutant. So rate of increase in the box, pollutant increase in the box. This is if it is this is basically a mass balance. So rate of increase in the box is equal to rate of pollutant entering the box minus rate of pollutant leaving the box minus the rate of decay in the box. Okay. So if you solve this, you will get an equation like this. Okay. So this is general equation. So for steady state condition, so concentration change with respect to time is considered as zero. So these are the equation you will get. So and some pollutants that such as CO and NO. So these are conservative. So and they generally not decay. Okay, so the K value is zero for them. So in that case, this equation will help you to calculate the concentration of those pollutants. So these are already discussed. So this the numericals and all. So you can go through this. So these are also available in the the drive link that is shared in that is already shared. So you can see this. So yeah. Next we learned about different um, like like air pollution controlling devices. Okay, so like gravity settler. So this is a schematic diagram of a gravity settler. Okay, so where gas is flowing in and it is flowing out. So this is width of the settler, height of the settler. Okay, so these are the efficiency you have to calculate. So efficiency you have to calculate. So these are the efficiencies are given here. So for block flow and the mixed flow condition. Okay, so these are the equations. So so this equation. So parameters are given. So you can see. So using this equation, you have to calculate what is the concentration. Sorry, what is the efficiency? Mm. See, for this case, compute the efficiency diameter relation for a gravity settler that has height this much, length this much, so average velocity is this much. So assuming Stokes, so basically in gravity settler, the Stokes law is followed for to calculate for the settling of the particles. Okay, so if you calculate using this, because this is the equation. So for mixed condition, 1 minus exponential of this parameter, this n. So L into G d square rho particle divided by 18 mu h. So this is so if you calculate this, you will get this much. This is the efficiency. Okay, so this is for uh, gravity settler. So here the air is coming and it is coming at a certain velocity, and the larger particle will settle due to gravity. So within this length, so it will settle and the cleaner air will pass through this. So this is gravity settler. And for cyclone in this case, so centrifugal force is used to separate the particles from the gas. So this is the so this is W is the width of the inlet, and H is the height. So dry dirty gas, it is coming like this, and this is centrifugal force is used so to separate the particles from the gas, and the solids are like it are the solids particle will hit the walls and it will settle at the bottom, and clean air will come through this and this is the outlet. Okay, so this is a cyclone separator. So these are the equations for to calculate the this eta equal to 1 minus exponential of this pi n into vc. N is number of turns. So in question it will if this type of question if this type of question comes, then this number of turns it will be mentioned. Okay, Then V so n into Vc d square is the size of the particle, average size, and rho particle is density, Wi is inlet, like width of the inlet, and this. So these are the equations. Okay, so using this equation you can compute again assuming Stokes law. So compute the efficiency diameter relation for a cyclone separator. So values are given. So particle size 1 micrometer, and viscosity is given as this much centrifuge. So you have to calculate. Okay, so again one more thing is another thing is d cut. Okay, d cut is the cut diameter. So that is nothing but at which size, which particle size that will be removed 50%. Okay, 50% removal efficiency, that size of particle will show 50% removal efficiency. Okay, so that is d cut. So this is the equation for cut diameter. This you have to remember. Okay, if so straightforward numericals may come. Yes. Okay, okay. Yes, yes. This is one of the review paper. Okay. So these are the biological treatment methods. So there are like works are already going on. This is contaminants of emerging concern. So you can check whether if you want to work in biological process or otherwise any other process. So different processes are there. See, okay. Okay. So cut diameter you have to this equation you have to remember. Okay, so 9 Wi into mu. So 2 pi NBC rho particles. So these things are I took from a book called from Indy Novers. Okay, so air pollution and control by Indy Novers. So this equation you have to remember to find out what is the size of the particle that will show 50% removal efficiency in cyclone separator. Okay, so see from this numerical cut diameter for a cyclone with inlet of this 5 inlet with of this. This is the velocity, and n is number of turns 5. Okay, and viscosity is this much and density is this much. So if you calculate, you will get, okay. So d cut you will get this much. So 5 micrometer size of particle. In this condition, 5 micrometer size particle will show 50% removal efficiency. Okay, so next is electrostatic precipitator. Okay, so in this case, so in electrostatic precipitator for removal efficiency, you can get from this equation. Okay, so this equation. So in eta is equal to 1 minus exponential of W into A by Q. A is collection area, so area of each plate. Okay, this plate areas. Okay, and W is the velocity, drift velocity. Okay, W is the drift velocity. So if you have to remember this equation to find out what is the removal efficiency of particles from electrostatic precipitator. Okay, so For previous problems, if you see like if you take trip velocity of this, and then you will get. So we have already solved several problems from electrostatic precipitators. Okay, so there's numericals you can see, so you can practice to find out. So it will help you. The different. So this is one problem from electrostatic precipitator. Okay, so the drift velocity you have to like flowing rate is given, and drip velocity is given us with this the help of this equation. Drip velocity is given. Okay, and the plate area required to collect this size of particles. So in this relation, if you put the size of the particles, okay, in micrometer, micrometer is given, so it is converted into meter. So you will get in meter per second what is the jet velocity, and you have to just for 90% efficiency, if you put the values here, so jet velocity value and efficiency value, so and what is the flow rate, q is the flow rate. So if you put these values, you will get what is the area. So like that, many numericals we already discussed. Okay, so there are many other like air pollution controlling devices, like filters are there, scrubbers are there, and condensation processes and absorption processes. So different processes are there. So you just go through this uh, processes. So, so numericals related to this processes. So we already discussed this numericals. So if you have any difficulties understanding, so hope you have like went through the PPTs that I shared in previous interactive sessions. Okay, so go through this go through this PPTs. So and recorded lectures and interactive sessions are available. So you will like I hope you will understand this numericals. Okay, so this kind of numericals you may get. Okay. Yes, and one more thing, this for this inventories, this transport emission inventory and all. So the other like other emission inventories are also there. So the name of this like models. Okay, so name of these models. Try to memorize this because you can get questions from this. Okay, from this name of this model. If you remember, you can get a few questions from this inventories also. Okay, so like this COPERT, this this model is used for which purpose, like that. Okay, if you go through the this PPTs, this important portions are already highlighted here, and if you go through this PPT properly, you will get many straightforward MCQ questions, and numericals are already discussed. So I don't think anything will come beyond that. So you prepare well for your exam. If you have any questions in if you face any difficulties understanding any numericals or not, so you can tell. Yes. See, like in my topic, it was biological process. So different removals, I have done in, like it was based upon wastewater treatment. Okay, so in wastewater you will get what COD, BOD, and nitrate, ammonia, nitrogen, nitrate, nitrogen. So this thing will be there. So the removal efficiency, removal efficiency you have to calculate. So the like for a reactor, if you are designing a reactor, so that reactor is giving you how much efficiency you have to, like there are colorimetry analysis, colorimetry methods to find out the concentration. So spectrophotometers are there. So these are for you have to monitor the dissolved oxygen and like pH. So for that different instrument probes are there. So you have to monitor like that. Okay. So for wastewater, see the purpose is like if your purpose is different, like if you are working in emerging contaminants. Okay. So that will present in a very less concentration in the wastewater. So in that case, you have to use to monitor that concentration coloring by colorimetry. You cannot measure. So in that case, you will use some like other instrument like HPLC, so, the liquid chromatograph, like that. Okay, so it basically depend upon your purpose. Okay, so in which pollutant you are working in. Okay, so yes, yes. Yes. So you have any like question related to this, like whatever is taught till now? So any questions from the numericals or the like any, any other like PPTs and all? So if you have any question, you can ask. Okay. Okay, then I will close the session for today.